This is a video for one of my all-time favorite types of problems in chemistry, limiting reactant problems. This is number 1 from your limiting reactants homework assignment, and might be a little bit of a lengthy video because these problems do take time. Essentially we're doing, and by the end of this we're going to have done 3 mass-to-mass calculations, which probably by now you know are the lengthiest of the stoichiometric calculations. So we're going to do that 3 times over the course of solving this problem. All right, so let's get into it. The number 1, this question, the chemical equation is CH4 plus 2O2 yields 2H2O plus CO2. So remember, in any stoichiometry problem, we need to have a balanced chemical equation. Sometimes it's given, sometimes it's not. Sometimes it's balanced, sometimes it's not. This one is given and it's already balanced, so we will be using this. The question says, how many grams of water can be produced when 50.0 grams of methane is mixed with 50.0 grams of oxygen? So what we need to do is, basically we're going to do 2 mass-to-mass calculations. The first one we're going to do is figure out how many grams of water could be made with 50 grams of methane. So that's going to be one mass-to-mass calculation. And then we're going to do another mass-to-mass calculation where we see how many grams of water can be made with 50.0 grams of oxygen. Okay, so what I like to do is, with the balanced chemical equation, I like to write down the amounts that were given. So we have 50.0 grams of methane, so this is methane. So I would write 50.0 grams to say that I have 50 grams of that. And then we also have 50.0 grams of oxygen. Here's oxygen. And what we're trying to figure out is how many grams of water. So this is the one that we're trying to figure out how many grams we can produce. So we're going to do one stoichiometry problem converting grams of methane to grams of water, and then the second one converting grams of oxygen to grams of water. All right, so I'm just going to start out with methane. Doesn't matter which one you do first. But we're going to set up a mass-to-mass problem. So I'll go kind of quickly through the mass-to-mass setup. If you're unsure of how to do this, watch the mass-to-mass tutorial video. All right, so first we need to convert mass to moles. So I'm going to have grams of CH4 in the bottom to cancel, moles of CH4 in the top, and this is where we need the molar mass. So I know it's going to be 1 mole, because anytime I use numbers off of here, it's 1 mole. So CH4, it's going to be 1 carbon, 4 hydrogens. Type that in. We get 16.05 grams. That's our molar mass of methane. Another conversion to convert moles of methane, cancel, and we want moles of water. And this is the part where we use the numbers from the balanced chemical equation. So moles of water, there are 2. Moles of methane, there are 1. Mole ratio. All right, and next I want to convert moles of water to grams of water. So if I have 1 mole of water, I need the molar mass of water, which maybe you have memorized. This is 18.02. 2 times hydrogen plus oxygen. All right. Yeah, that was a little fast, but hopefully that made sense. So that's our first mass-to-mass problem. So now we'll calculate this. 50 divided by 16.05 times 2 times 18.02. And we get to use 3 sig figs because of these. So we get 112 grams of H2O. Now I'm not going to put a box around this yet because I don't know if this is the answer. This is how much water we could produce from 50 grams of methane. What we need to do now is figure out how much water we could produce from 50 grams of oxygen. So I'm going to set up that problem now. So now we're going to start with 50 grams of O2 and do the same thing, convert grams of O2 to grams of H2O. Okay, so the first thing, I know grams of O2 needs to cancel. So I'm first converting grams of O2 to moles of O2. So I know that 1 mole of O2 has a mass of 32.00 grams because it's 2 times 16, molar mass of oxygen. And my next conversion factor is the mole ratio from the balanced chemical equation. So we are converting moles of O2 into moles of H2O. So moles of H2O, remember from up here it's 2. And moles of O2 is also 2. And then the last step is to convert moles of H2O into grams of H2O, which we actually already did up here. So this is the nice thing about limiting reactant problems, is sometimes a lot of the work for molar mass calculations has been done for you. So always look back in your work because you might be able to save some time. I already had the molar mass of water, and actually that's the one a lot of you probably have memorized already. But in longer problems, it might be helpful. All right, so now we can calculate this one. 50 divided by 32 times 2 divided by 2, those cancel, times 18.02. And again, we're allowed 3 sig figs, so it's going to be 28 point. This is going to round up to a 2 because it's followed by a 5 with some other stuff. So we get 28.2 grams of H2O. All right, so now we essentially have 2 answers. Okay, so this is where limiting reactant problems can get a little tricky. If we had 50 grams of methane, we could potentially make 112 grams of water. If we had 50 grams of oxygen, we could potentially make 28.2 grams of water. So the question is, how much water do we really make? To think about this, you need to realize that one of these things is going to run out. The oxygen can only make 28.2 grams of water. Even though the methane can make way more water, we're going to run out of oxygen because we mixed the 50 grams of methane and 50 grams of oxygen. So when you get to this point where you have your 2 answers, the real answer is the smaller number because this is the one that runs out. O2 will run out. It can only produce this amount and then it's done. You can't make any more. So this is our real answer to the question, how many grams of water can be produced? And I would, my recommendation for you is to cross out the other answer. I mean, you don't have to be obnoxious about it, but just so that you don't accidentally use that for something else. Okay, this is the answer. The other answer, you just needed to verify that this is the correct answer. This number's too big. So even though you can make more methane, you run out of oxygen. So that's the first part of the question. Second, and part C here says which is the limiting reactant. So remember, your choices for reactants are either methane or oxygen. The one that's limiting is the one that stopped your reaction. Which one ran out? Well, we just said that this one ran out because it produced a smaller amount, right? So the limiting reactant here is oxygen, or O2. O2 is the limiting reactant. Methane, you had some left over. You could have made more water. And that ties into the last question, which reactant is in excess and by how much? So methane is in excess, and so what we need to do for this last part of the problem is to figure out how much excess methane we had. And to do this, there's a few different ways you can do this. The way I'm going to show you here and in class is to start with the amount of water that we produced. So what we're going to do is we're going to take this number and we're going to say if we produce this much water, 28.2 grams of water, 28.2 grams of water will require how many grams of methane? And then once we do our mass to mass calculation, we'll be able to see how much methane was used to create the 28.2 grams, and we can subtract that from the amount we started with. Okay, so essentially what we're doing for this last mass to mass calculation is we are going to convert 28.2 grams of water, because that's what we produced. We're going to convert that into grams of methane to see how much methane was required to produce that amount of water. And then once we get that, we'll subtract it to see how much was left over. Okay, so we're going to do one more mass-to-mass problem, starting with this 28.2 grams of water. So we'll first need to convert this to moles of water. And we know that the molar mass of water is 18.02. We did that here, or you already have it memorized. And that's for 1 mole. So we first convert mass to moles. Now we convert moles of water to moles of methane, because that's what we're trying to get to. So moles of water will go on the bottom, and moles of methane will go on the top. And remember, to get these numbers, we'll look at our balanced chemical equation. So moles of methane, here is 1. And then moles of H2O, here is 2. All right, so there is the mole ratio, and we'll continue with one more conversion factor, because we need to convert now moles of methane into grams of methane. And the nice thing about the last mass-to-mass calculation you're doing is that when you need the molar mass here, you've already done all the work. So if you check up earlier, you've already calculated the molar mass of methane there, 16.05. All right, so now we will do this calculation. And we're allowed to use 3 sig figs here. So we get 12.6 as our answer, because it's a 5 followed by 5 with other stuff. So 12.6 grams of methane. So don't get carried away here, because that is not the answer. So think about what you just calculated. You just converted 28.2 grams of water. We just figured out if we want to produce this much water, how much methane will we need? This much. So what we just did was we calculated the amount of methane used. If we have 12.6 grams of methane, we can make 28.2 grams of water, and that's how much we made. The question is asking how much is in excess. So we want to figure out how much methane is left over. So to do that, we need to refer back to how much methane we started with at the beginning. We started with 50 grams. So of that 50 grams, we only used 12.6 grams. So the last step is subtraction. So we're going to take 50 grams of methane. We only used 12.6 of those grams. So we want to figure out how much is left over. So we just do 50 minus 12.6. Remember, your sig fig rules for subtraction say that since this is to the 10th place, this is to the 10th place, our answer should be to the 10th place. So it's going to be 37.4 grams methane in excess. And that is our final answer for this problem. So it's a very lengthy problem. It required you to do 3 complete mass-to-mass conversions, right? So good luck with the rest of the assignment. They do take some time.